let's kick off. So first of all, we're a public company now. You know, we floated on the stock market a couple of years ago, and I have to give a warning that I'm not making promises, and you shouldn't buy or sell stocks and based on what I'm saying, and there's obviously uncertainty around R&D, all the usual stuff. It's on the screen there. That's called a safe harbor statement. So our goal as a company, our sort of overarching statement has been to try and enable anybody to sequence anything, anywhere. And that's quite an ambitious goal. And how far, I think this is year 9 of this conference now, year 9, next year is 10 years. So how far along are we on that goal? Well, actually pretty far. And there's some examples on the screen here, high-profile ones that you've probably seen on various media, including social media. And we've had, for example, Stanford doing the fast, I think it's still the record for sequencing a human genome for a newborn baby. I think that can be a lot faster, and they're working on that. They are working on it. And we will help with that. There are some very large operations now running many Prometheans. Spoke today, in fact, over in UAE. And then we've had people field sequencing, and the very high-profile sequencing on the space station. It's very nice. And then we've had African farmers sequencing their crops, looking for pathogens. So pretty good progress towards anybody sequencing anything, anywhere. But it's still not there. It's still too difficult. The devices are not cheap enough yet to enable people in resource-poor countries to really get stuck into this. We haven't decoupled them enough from the lab. There's still too much lab dependency baked in. We need to break that. So there's still a lot to do. So I'm going to talk about some of the things we're doing to enable that. And as ever, you can go back and look at previous talks we've given in these conferences. And it's important because, as I said maybe 3 or 4 years ago, there's just too much stuff now for me to talk about on the stage. In the early talks, I could cover everything. So, for example, I'm not going to talk today. We've spoken previously about protein sequencing. We're developing a method to sequence proteins to basically disrupt mass spectrometry-based proteomics. I'm not going to talk about that today. There's been very substantial progress there. We believe we're ahead of the academics, but I'm not going to talk about that one today. Right? We've spoken previously about what we call our outie chemistry. That's where we catch a small molecule, and we can sequence a molecule as often as you like. We pull it out, we drop it back, we pull it back. You get multiple copies, very high confidence mutation detection on rare molecules, targeted at needle-in-a-haystack applications. It's all going really well. I'm not going to talk about that today. And we've spoken previously about what's called a FET array. That means a field effect transistor array. It's a new kind of sensor where you can have thousands or tens of thousands of very sensitive channels measuring voltage rather than current. It's a completely different architecture of sensor. That's all ongoing. I'm not going to talk about that today either. So I'm going to talk about other things. But if you go back to my previous talks, I want to assure people all those things we've brought up are ongoing areas of active R&D, which are all going quite well. But I'm not going to talk about those today. So you're very familiar with the technology. I usually show this slide. It just gets me warmed up. You know how it works now. We have a membrane system, a proprietary chemistry that we developed. We have a pore that we engineered. It was based on a pore that came from VIB. And then we have it was a secret for a long time. We have a motor, which is a helicase. Everybody else was using polymerases. We couldn't get polymerases to work well enough, so we went for helicases. And then we've engineered a helicase. And the system you're familiar with is what we call strand sequencing, where you put on, when you do the library prep, you attach the motor, goes in the flow cell, and it sequences, and the DNA goes into the pore, it goes in, and the fragments can be very long. So you're all very familiar with that. So let's talk about Duplex. And we revealed this a while ago. I can't remember when now, but it feels like more than a year ago. We've had various attempts to sequence both strands of a single molecule, and the earliest one we did was where we attached a hairpin on the molecule and we'd sequence both strands. And we abandoned that approach, and I think I gave a talk about that. And it's partly because there are some artifacts in the signal caused by having the hairpin there. You'll get distortions in signal, you get uplift. We found that the movement of the helicase on the complementary strand isn't very good, and it's even worse when you have a hairpin applying a force to it. The hairpin might apply 20 piconewtons of force, as well as the current. But most of all, the algorithms we used in those days didn't cope very well with that kind of data. So we never really got the uplift from it, and we sort of abandoned it. And then one day, I pulled one of our senior researchers into the office, and I said, well, what if the complement follows the first one at some frequency? What if it follows the first one? And I said, have we ever looked for that? And no, we never really looked to see if the complement's following. So we went off and had a look. And about 1.5% of the time, the complement would follow the first strand naturally. So we thought, well, we can optimize that, we can enhance that. And initially, we just changed the adapters. We just fiddled with the adapters and made the adapters a little bit sticky. And that got us to around 30% duplex rates, which is pretty good, given it's the standard double-ended ligation that most of you probably use at the moment. So on this new system, as shown in this diagram, the first strand goes through, and the second strand, with a bit of coaxing, will follow it. And then we get a very nice clean first read, and we get actually a better second read than we got from the old hairpin-based methods. And that was quite gratifying to see. And then, of course, as you all know from previous talks, we've spent a lot of effort over the past few years developing these machine learning methods for base calling, using very similar technology developments that are used for things like ChatGPT. It's all been going on out there for other purposes. And we've really rolled those enhancements into our base calling. We have a very strong ML team now. So we came up with a way to jointly call the signal from both strands. And that's we called it stereo. It's obviously an allusion to 1970s music equipment, which other people do. But we call it stereo base caller. And that's now working very well. We revealed this a while back, and then we've spent the past, I don't know, whatever it is, 9 months or so, really working to get the numbers up. Because we know that expectations are very high for duplex. So Lakmal's team in particular, and others, many of them are here at the conference, have done a huge amount of work getting the duplex numbers to be really, really competitive. So where we are now, and we are actually going to be releasing duplex at this conference, so this week, so today, you will be able to go on and sign up for getting hold of high duplex, or as I called it, super duplex. And where we are right now is we can get around 85 to 90% duplex rates. Right, so pretty much the vast majority of the DNA you put in on a duplex system will become a combined read of the first strand and the second strand. So that's good, and it's going to be very hard. Maybe we can get a bit more, maybe we can get 95%. The team are here, I bet if you ask them, they'll think they can get 95%. So we've got the rates right up from where the prototype rates were. And then what we did is we asked, I said, well, people complain, that's a high watermark, that number. So we got a group of recent recruits to Nanopore, naive users, you might call them. They're going to be graduate, postgraduate lab people, but they'd never run duplex or even the ligation kit. And we got them to do it. And this little polar plot shows that one of them got 85, 90% duplex. Two of them got sort of 80% duplex. And sadly, user number 3 did quite a poor job for whatever reason. So that might be a representative sample, sort of feel of what you'd get on your first run. I'd hope your second run would be better. But it's certainly possible for naive users to get pretty good duplex rates using the same methods that we're using at the moment. Now we've also, again, incremental advance. There's two forces in this game. One is dramatic changes, that's innovation, and the other is incremental improvement. And they've been slaving away, and we've now got the duplex accuracy to around Q32, or the peaks around Q32. So we've gone up from Q30 to Q32. And importantly, that's at what we're calling 5 kilohertz. So we're rolling out as well at the moment, I think it went out today or yesterday in Minnow, the capability to run at 5 kilohertz. Now that number is how many measurements we take per second from the flow. Right? So I think most of you have been at 4 or 3 kilohertz for the past 8 years or so. We're going to 5 kilohertz now. And because of tuning and software improvements, that just gives us a little boost in quality. So we've nudged up a little bit to go to Q32. And you can see on the plot here, you've probably seen these. You've got an older Kit R9 Simplex at the bottom. Then you've got a Kit 14 Simplex, that's the current chemistry. And then at the top, you've got a plot of Duplex. And everybody tells me, people who've been using it say, it's great, love it, really good for assembly in particular, and so forth. So substantial improvements. Now again, with Nanopore, there's no relationship really between length and quality. So if you have a 100 kb duplex read, it's going to be the same quality as a 400 base duplex read, more or less. Because we're not using a light-based chemistry, so we don't damage the DNA as it runs. As I've said many times, if you can deliver the fragment to the pore will consume the fragment. And as long as there's no backbone breaks or interstrand crosslinks, it will go through and Bob's your uncle. And you can see here our simplex rates. I'll talk about this in a minute. We've been improving those as well. But modal simplex is now around 99.5%. So even the best simplex is actually getting close to Q30, some of those simplex reads. And that's all at 400 base per second, 5 kilohertz. That's the condition that we're releasing at the moment. So that's pretty good news. Our longest perfect read there is 40 kb. Our longest Q40 read is 130 kilobases. And as you can see, an interesting point here is this is all double-ended ligation. Now, what I would like is ultra-long duplex, but that's quite hard because you have to get, at the moment, you have to get both ends on. So it's an unsolved research problem, is doing that, or doing something else, something that doesn't require ligation. But I think ultra-long duplex is the next big challenge. So that's not our best data, but here is, for example, native human. And on this run, again, it's a high watermark run, we got almost 150 G out of a Promethean cell, which is not that untypical these days. People generally get over 100 G. And then off that, if you look at the bar chart on the right there, the one called Duplex called, that's what you get out when you, out of the base caller. You get over 50 gigabases of duplex from native natural human DNA. And you're left with about another 45 gigabases of simplex. And I've seen correspondent speculation out there. People think the simplex is junk, it's like that PacBio CLR stuff. It's not. It's Q20 plus simplex. It's really good. It's really good for mutation detection. But you've also got 50 G of duplex as well now. So that's a human genome's worth of duplex and simplex from one Promethean flow cell. Now, it's natural DNA, and I think we're the only platform that can actually measure natural DNA. I think all the others amplify before or during the sequencing process. And we are strongly of the opinion now that natural DNA has a lot of interesting weird things on it. So we know it's modified, it's probably damaged. We think it can be damaged by the extraction. You get backbone breaks, you can get bulky adducts, you can get interstrand crosslinks. All of that is in natural DNA. And when you PCR it, the PCR effectively removes or filters all that stuff out. So natural DNA is difficult, but very pleasing to get 50 G of natural DNA from a single Promethean flow cell. So all the modifications, if that's what you're looking for, are going to be in there. All of the damage, if you're looking for damage, I think that's an interesting thing, is going to be in there. It's unchanged. Now, so we are very short, well, now you'll be able to go onto the shop and obtain this. Software-wise, there's a version of Dorado. Now, Dorado is the new offline base caller, replacing Guppy. That went out today, in fact, about 2 hours ago. And that's fully capable of doing duplex calling in a very automated way. It's very slick, very optimized. Have a look at the tweets on that. It's also now very performant. The team there have really made it quick enough to be useful. We anticipate that we will fold that into Minnow before July. So there might be a bit of a wait for Minnow users. So at the moment, we're base calling sort of offline or adjacent to the sequencer. It will get folded into Minnow by July. And you're probably familiar with Minnow now. In Minnow, you can turn on various features, and you'll be able to turn on duplex and turn on modified bases. And it will have lots of nice graphics in. But the key thing is it will write out the relevant files. It can work from Pod 5, and it does all the pairing for you. It's completely automated. So although it's a command line thing at the moment, it should be pretty straightforward. I'm not going to tell you how to do your day jobs. Lots of people have reported, you know the advantages of duplex. A lot of it's around assembly. There is high accuracy single molecule, lots of utility. I don't need to sell that because people are doing it online and using it. So it's available right now. You can go into the shop and you can sign up and get duplex. And we're doing a sort of soft commercial launch. So there's introductory pricing, which is cheaper, not more expensive, it's cheaper. We're very keen to make sure this goes well. That's why we did the validation. That's why we put all the work into the performance. And we're going to do a very supported launch of this. So, for example, if you say, well, I rely on Minnow to do my base calling and blah, 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 they're probably going to tell you to wait till July. But if you've got some bioinformatics capability, they'll probably be fine. You can crack on with duplex. Now, importantly, the flow cell is marked. Duplex is a special flow cell. So it's marked up with a HD. So if you use the standard kits that we have, the ligation kit, on that flow cell, you're going to get duplex. So if you don't want duplex, you need to use an ordinary flow cell. We do have a way to turn off duplex. We do have a way to turn it off. But that isn't being released at the moment. That will come in the future. So you just want to be clear about what you're getting and what you're using it for. Now again, we did a sort of pre-early access thing, really, or early access. And you've heard, again, I don't like presenting other people's work. I'll refer to it. You've heard these talks. You've heard the T2T talk. You've heard the others where people have had a taste. And the version they were using was an alpha version. It was lower throughput. The base callers weren't as good as the one we're using now. So even on a sort of ropey version, they still got lots of utility out of it. So the version you're getting is quite a big step up from this version. I hope that's clear. Now, how can we get more duplex? I know what you want, and we'll talk about that in a minute. There are lots of ways to do this. So the main thing you need to do is get both ends on, obviously, because it's adapter dependent. And actually, we found that with the kits and the protocols, our naive users are pretty good at getting both ends on. And a lot of it is down to what we call blocking, which is a bit of a misnomer. But for the reasons I said earlier, natural DNA is odd, and most people don't look at it. And it's a miracle, really, that this works at all, Strand, if you think about it, that you can zip that much DNA through a hole without something going wrong for 3 days. It's quite pretty impressive, isn't it? But very rarely, something does go wrong, and it will block, or you can't unblock, or something will foul up, and you'll lose a channel. And over time, you lose more channels, and then your throughput drops. So there's a lot of headroom there to fix that and get more data out. And we currently get only about half the data you can get from a Promethean cell. Even with a current cell, you only get about half. because of that effect. And so a lot of work is being done now internally to remedy this, and we have some really intriguing early results I'm going to come on to later about how we can just take the existing system and uplift all of the throughput numbers. But a lot of it's about natural DNA and dealing with the weirdness that comes from that. Some of which may be extraction related, actually, interestingly. It might be down to extraction. One interesting thing we've looked at recently, there's a graph later on, is this is going to sound obvious to you, but it turns out that buffers have quite a large impact on this behavior. And you'd think that'd be obvious, but actually it's only recently that the system has become so good that we can measure very small effects like buffers. And so we've been changing buffers on the trans side and the cis side, and we're finding they're having quite large positive impacts on things like blocking. So I anticipate in the near future quite large uplifts in the amount of data that we can get out of the system. Now, when you PCR something, there's a reason, in my view, that Illumina missed 8% of the human genome for 14 years. And it's because they smash the DNA up and then they amplify it, and then they read the complement with effectively a PCR system. Now, if we PCR things, all the weirdness goes away and you amplify all the good stuff, and then we can get 100 G of duplex out of a flow cell, over 100 G. And yes, in this run, it's 100 G of duplex and another 50 G of perfectly good Q20 simplex. So you're getting really high quality, large amounts of high quality data. And 100 G of duplex is a human genome's worth of, if it was amplified, or if we fix the problem with natural DNA, that's a lot of duplex data. So we think this has crossed the threshold now where it's attractive to launch these kind of numbers. And we're pretty confident that you can get those kind of numbers. And the key message is we are going to improve this incrementally over time. And remember, we don't need to change the machine. Don't need a new box for this. We can just continuously innovate and incrementally improve what you've got, and it gets better and better. That is really the story of Nanopore in a nutshell. Now, Simplex itself is pretty good. I want to point this out. It's improving. We're moving to this new 5 kilohertz sampling condition. And you can see the different base callers here. It confuses people, I know, and I apologize for that. So there's a very fast base caller, if you want a quick answer. There's what we call the high accuracy base caller, and there's what we call the super accuracy base caller. And the only difference is they're just bigger neural networks. And the super accuracy really milks all the value out of it. It really gets, there's very little incremental return from having a bigger network than the sup caller. The downside of it is computationally quite intensive. The hack caller, it gets you 99.5% of what the sup caller gets you, but it does it in 1/10 of the time. So really the practical one is the hack-based caller. Now, if I was you sitting there, I'd say, yeah, that's great, Clive, but I want to use sup all the time. I just want you to speed it up for me. That's what I'd be thinking. I mean, why would you detune your car? Maybe some people would do that. I wouldn't do that. So anyway, it's still extremely good. And we get very high yields of both native and PCR simplex data above Q20 modal, and you can pick the base caller that suits your needs. My voice is going. Now, Simplex is actually very good, and I don't need to tell you this because most of you are using it, but one of the key things for sequencing, probably, I don't know what number, pick a number, 85% of applications are really about mutation detection, or counting things, or identifying things. And there are referenceable papers now, and this is not just me talking. A single nucleotide variant detection, you've heard people talk about it at the conference, is extremely good on Simplex now. Indels is what we mostly get criticized for. And those mostly these days come from the edges of long homopolymers. In fact, it's homopolymers longer than about 9. But those don't tend to occur in coding sequences in human anyway, so our indel performance is actually quite good. There's work to do. You can decide the relevance of homopolymers. We're going to fix it, but you can decide. And then, well documented now, our SV work is, pretty good. So actually, Simplex does a lot of work. There's a lot of heavy lifting, in fact, even in the current form. Don't underestimate Simplex. And actually, if you look at a hack or a sup called Simplex, there's a tiny difference in the mutation detection, if you do a comparison. It's only really indels that are slightly worse with hack versus sup. But you're free to decide that for yourselves. Now again, this is all now well documented. I don't need to sort of present other people's work, but there's a wide variety of things, and people talking here today about the utility of Simplex. But it is improving. That's what I want to tell people. And here's a little performance sort of slide. So our view is, so we currently get about half of what you can possibly get out of a flow cell. And I think we can claw that back. We can probably run a bit faster. We can probably finesse the runtime. So our best run ever, I think, was 250 gigabases using R9. I think we get about 190 or more from R10. Our target now is to get towards 400 gigabases. That's all on the current Promethean cell, and equivalent uplift for Min9 as well. Neglect Min9, but just scale it, same stuff. Now, at 400G per flow cell, Promethean, you're looking at nearly 20,000 human genomes per year. Most of you aren't doing human genomes, fine. But the point of this is that there is a lot of headroom in the current system without changing the instrument, to really push up the numbers and really drive down the costs. The capacity is there to get to a $200 human genome on Promethean. It's there already in the system, mostly down to us optimizing the chemistry in the flow cell. Again, no new machine required. It's all on the system you have. And this is one of the major targets for Nanopore over the coming year or so. I've said before that when you buy a Nanopore system, I said it was an investment in the future. And what I mean is, because we don't need to make new boxes all the time, and because we have a modular system, a modular chemistry, and because there's just more and more value to mine out of that system all the time. Now, another feature, a long time ago, at 2012, I spoke about a feature called Run Until. And somebody joked with me earlier. They said, I met you 8 years ago and asked you when methylation calling would be there. And you said, it'll be there next year. That was 8 years ago. OK, my time estimates aren't that good. But actually, I spoke about a key feature in 2012 when we launched this technology called Run Until. And that lets you pre-program a targeted result in the sequencer. So it's more and more common now for people to run more than one sample on a flow cell sequentially. So now built into Minnow, you can say, I want 10G of this bacterium. And then you can stop that and load a different sample and say, I want 13G of this sample. And it will handle that logic for you. Most of you are pretty familiar with adaptive sampling. So that's where we can, as a molecule goes through the hole, we can live base call it before it's gone through, and then you can kick it out again. So rather than going through 130 kb, you can kick it out and catch a different molecule. And so it's an on-platform enrichment method. And that's now available in Minnow for P2, for people using P2, all automated. Very useful for panel enrichment, targeting a region, barcode balancing. Again, so more and more of our features now are being pushed into Minnow and being made easy and accessible for everybody. So I'll change gears slightly and talk about base calling. It's quite a big topic. So the team really want to emphasize this because they've done a huge amount of work in speeding up base calling in Dorado. Remember, Dorado is the sort of development test bed that's available publicly, where we do all the methods of development. And here you can see some performance plots. So the big news here is that the hack, remember I said there isn't much difference between hack and SUP in terms of mutation detection. But hack now keeps up. So on-device keep-up base calling is possible for a P24, and of course min-I and all is far downstream from that. But hack can now is much better for if you're running all your flow cells all the time. Now a lot of people don't do that. They run 5 today, 2 tomorrow, 12 Wednesday. Most workflows are quite lumpy for most people. So I'm not sure that many people run sequences at full capacity back-to-back anyway, whatever they are. They would deny that probably, because they had to pay a lot of money for it. I'm skeptical. But anyway, you can now run 24 Promethean flow cells and get hack Q20 plus data out, so that's pretty good. Now, we have a software package. You've probably been downstairs into the, what's it called, the Bat Cave or the something cave, and it's called Epitome. Again, like a lot of these things, it started off as a very modest piece of software, but it's really gaining a lot of momentum, and it lets you do automated bioinformatics tertiary analysis. You can do it cloud-based, you can do it local, it's transparent, you know what's going on, you can look at the stuff, and more useful workflows are being put into that. It's mostly open source, unlike competitors, still going with that. And there's a lot of example pipelines in there. Do check it out. And if there isn't something in there that you want to automate or semi-automate, we can put it in, or you can put it in. It's now got real momentum behind it. And it's very good, remember, because I said we have to have, we're making small, cheap devices. So very often people who want to use them don't have the bioinformatics skills that large labs have. So this is a key strategic thing for us to get this right. So do have a look at it. It's really quite slick. And there's a version coming, we're getting more and more traction with clinical. We can turn a version of this into a click workflow for clinical. That work is ongoing. So it's really becoming quite mature. Now, not spam, some meat, proper meat. Huge progress, some modifications. There's 2 ways to approach that, and we started off doing what everybody else does, which is CPG-based methylation. So if there is a gold standard in this, it's not really gold, is it? Let's face it, it's brass. There's a brass standard in this field. It's probably the chemical treatment, whatever you call it, bisulfite for CPG context. Fine. We started there. And I mentioned in previous talks, the goal for us, much more ambitious, is any modification in any context, what we call all context. And we are making really serious progress there now. So at the moment in Minnow, you can get 5-methyl-C in CPG context. You can also get 5-methyl-C and 5-hydroxymethyl-C in CPG context. Those are baked in now to Minnow. You can just pick them. A lot of positive feedback about that. But our ambitions go way beyond that. Because we can look at natural DNA, why wouldn't you try and get everything? And natural RNA. Somebody spoke earlier about RNA. Why wouldn't you try and get everything? So here are some confusion matrices for our methyl-C calling. And this is the CPG-based. And you can see our belief is that Nanopore methyl-C calling is better than bisulfite. Again, that's not an idle boast, but other people say that outside Nanopore. And now hydroxymethyl-C is also getting very competitive, as you can see from these plots. But the thing we're really driving now is any modification, any genome, which is music to the ears of people who don't work on human, people who work on plants, for example, and other bacteria. It turns out lots of things are modified. So how do we do that? Well, it was such an easy idea when we came up with it. It looked so easy. It actually turned out to be 2.5 years of work. we actually make synthetic random DNA. We make huge libraries of random DNA, and then we modify one position with a known modification, methyl C, whatever. We put it in one place. So we can make synthetic validation and training sets for the base caller. Often contexts that just will not occur in nature, probably. But nonetheless, we can correctly base call them. Adrian Leger's group and Marcus Stoiber over in California have done a lot of work on this. And again, you can now see that our models trained on synthetic DNA, these are not trained on reference sequences or anything anybody else has sequenced. These are based on, as close as we can get, sort of de novo. Extremely performant. In the old days, we'd be criticized for H. pylori, which is quite heavily modified. On a 4-base nanopore, non-amplified, it wouldn't look that good. But now we can call those H. pylori modifications, and it comes out a lot better. That's without PCR. That's natural DNA again. Very powerful. So the ambition here is to just knock down all the mods. Adrian has a list, and he's just going to work through it. And we're just going to add them to the base caller, and we're going to add them to Minnow. Again, no change of instrument, no change of chemistry. Just over time, more and more modifications will become available for base calling on natural DNA and RNA in Minnow. And these are the ones we have already. These are in Dorado right now. So the latest Dorado contains the latest models. And my bet would be, you're going to test this statement, my bet would be they're better than SOTA. So what's left then? What keeps me awake at night? Well, I was hoping to come here today and tell you that we'd fixed homopolymers, because really the only residual problem with Nanopore, in my view, please disagree, is just the edges of long homopolymers, typically longer than 9. And most of our consensus errors, not all of them, most of them come from that. And again, you can argue whether that's relevant or not. I mean, people clearly buy the technology. You're all sitting here. So it can't be completely not useful, can it? But if you want to do telomere to telomere, nanopore-only de novo genomes, we have to get every base right, every single one, including modifications and homopolymers. So this is a work in progress. It's not there yet, but it looks really promising. And I've mentioned it previously. I've spoken about it some years ago, and then we dropped it. We just got distracted by the priorities. We've circled back to it in the past 4 months or so. And what we do is, on a duplex system, we can do a synthetic complement. We can make a synthetic complement, just a complement fill. So 1/2 of the molecule is synthetic and 1/2 is natural. And we can spike in special reagents that will modify the homopolymers on the complement. I'm not going to say exactly what's going on there because it's a bit proprietary. But what it means is the basic problem with the homopolymer on nanopore is it's flat. So there's very little information in it other than time domain. Because of the way enzymes work, that's quite uncertain, a lot of variance on it. But we can disrupt that now. We can, in a targeted way, we can disrupt the homopolymer on the complement, and we can make it look like a complex sequence. And then the base caller can latch onto that and give you an accurate homopolymer length. That's the principle. Now, it's a research project. It's not ready yet. It's in progress. But again, it looks pretty promising. So my ambition for the rest of the year, wherever it is, whether it's Singapore or Houston or wherever it ends up being, is to come back with a pretty plausible fix for at least consensus homopolymers, if not single molecule homopolymers. And then you'll be able to do your telomere to telomere assemblies, nanopore only. That's the target for this year. Now, this is pretty good. So RNA, we've done a huge upgrade of RNA. And now there are people here who probably aren't that interested in natural RNA, native RNA we call it. It actually has a really little tight-knit fan base of RNA fanatics who think it's the best thing ever. Probably only about 5% of nanopore users, but we think it's going to grow. So when you enable a technology to measure something new, people see things, and then it just becomes interesting. I mean, 10, 12 years ago, if you'd spoken about methyl C or hydroxymethyl C, you wouldn't have got any traction. But now it tells you the tissue of origin for a cancer, right? And in plants, there's all kinds of things in plants that remain to be discovered about modifications. So RNA is really the next frontier for sequencing. And now that our DNA stuff's getting pretty mature, we're really focusing back now on RNA. So finally, for the RNA junkies here, we've done an upgrade. It's going out now, I think. You know how RNA works. It's the same as Nanopore, but it's a single strand. And we've launched RNA-04, which is a 2 times faster motor, so you get much higher throughput. And the most important thing is we've really boosted the accuracy now to where it's 95%. Now remember, RNA is often quite heavily modified. So we've got the same problem we had on DNA, but it's worse because the base callers will be looking for 4 bases and probably miscalling mods as errors. That's what happened in the early days of Nanopore until we learned to get around that. So in here is more value to be extracted from calling those modified RNA bases. The problem is there's at least 147 of them. How many do we think are relevant in DNA? 8, 9? DNA damage, another 5? 147 in RNA. It's quite difficult. But Adrian has a list. He has a list that he claims reflects the priorities in the research community. And using that same synthetic library method, making RNA with mods at known positions, we're going to knock down modified bases in RNA as well, just like DNA. But now this upgrade gives us a very good baseline system on which to start doing that. That's available now. Now, the other big thing we've done is we actually have a custom pore for this. Again, Lakmal and his team are wizards at making and finding pores. It's complicated having multiple pores, but if it pays, it pays. And Adrian's come up with this very nice plot here. And I like it. It's going to take me a while to explain it. Basically, if you have, it's looking at signal, intensity, standard deviation, that's noise, and the dwell. If your blobs there are symmetrical, they're the same. If they're non-symmetrical, you have a difference. So what he's showing here is that where we have no modifications in the RNA, we can see them in the signal, is what that plot tells you. It tells you there's information in the signal where the mods are. So they've been looking at lots of different mods, and all the mods they've looked at, okay, it's only like 8 or 5 out of 140, but all the ones they've looked at, they can see them on this pore. I don't think they're going to see all 147, but if the first 8 you look at are there, there's a good chance another 20 are going to be there, I think. So this looks a really promising system for measuring modifications in RNA. And I think there's his list. He put the list on what he's looked at, which he thinks are directly relevant immediately. So this looks really promising. We're going to have a cracking natural RNA with modification system. No change to hardware. Just same hardware, just software we change. That's it. Different pore, different flow cell. No change to hardware, no new box to buy. And they've chosen this example, and it's a bit of a niche example. It's pseudouridine, and it's actually the one used, this is going to get me in trouble. It's the one used in RNA vaccines. A lot of RNA vaccine developers are using Nanopore now. And they put these modified bases in to evade the immune system, and I think it boosts expression of the antigen protein. And it's quite key for them to be able to sequence it. I'm not going to pretend to be an expert on this. Obviously in production, in design, in quality control, if you're going to stick it in somebody's arm. My bet would be, although I don't think they've done this, my bet would be you could probably look at blood and see if there's any floating around in blood, because it enhances stability as well. But we can see this very nicely on this new pore. So there's already a pretty good RNA-based commercial application for looking at modifications in RNA. It's pretty exciting. The accuracy is shown. So that's RNA-004 shipping now, available now. Rosemary can update you on all the details. Please, if you're an RNA junkie, have a go. It's pretty good. Both platforms. I'm going to skip these slides, but I'm very conscious it's quite late, and everybody wants a beer, me included. So I'm not going to go on. People are yawning. But there's a really good slide right at the end, so just stick with it, right? You know what we sell. I'm going to tell you that. OK, P2 is out. Now, I'll apologize, first of all. Some of the very early P2 solos there had a hardware bug from a supplier. It was a bad board, all being remedied by swapping out the boxes now. It wasn't all of them. It was about 20% of them. It's all fixed. And now we're shipping the other P2, which I wanted to call Skywalker, but they wouldn't let me. I didn't choose the name for Solo. I know it's confusing. It's Rosemary. You want to take it up with? OK, but the other one is now shipping, and the other one has fully integrated compute. You can see that we're now cramming, as you'd expect, cramming more and more features into software that give you walk-away automation and walk-away analysis. So it's much less painful to run and own. You can think about it going into clinical applications. And that's the one on the left. The first one went out a couple of weeks ago to Josh Quick's lab, and others will become available over the summer. So this box is now in early access. Again, it's been used in field. You've probably noticed the nifty skins for the P2. Quite nice idea. And it's all out now and working. Some people getting spectacularly good results. Yeah, so it's all looking quite tasty. It's a released product. Now, how else can we boost output? So a lot of work's being done on engineering the motor. And you currently run at around 450 to 500 bases per second. That's the speed at which the motor puts DNA through the pore. We have found other motors that work quicker, up to 1,000 bases per second, and give relatively higher accuracy as well. That search is ongoing. So modular chemistry, quite likely we're going to swap out the motor at some point in the near future. And at 5 kilohertz, that's probably why we've done it. The groundwork is there. That means potentially more data from the current system at least the same accuracy. So engineering the motor is another way, apart from removing blocking, that we can really push up the performance of the system you've got right now. That's all in progress. Now, a neat trick here, I said buffers. This is quite a nice one. So it turns out that, again, we can measure very subtle effects now. By the way, light can affect what goes on inside the flow cell. I'll just tell you that one's coming. Very small effect, but light, yeah, light. Amazing. By changing buffers on the trans side, we can have quite a large impact on output from a Promethean flow cell. It doesn't look it on this graph, but actually, if you look at the current buffer, you're getting about 80 G. And on the new buffer, it's getting close to 120 G, just from changing buffers. And we think what that's probably doing is, what we think happens is you get some secondary structure formation on the trans side. We think it's G quadruplexes. And a different buffer will stop that from happening. And then you can kick the molecules out better. So it actually deblocks better. It's not blocking change, it's a deblocking improvement. And that's a really easy change for us to roll out in the background without upsetting anybody. You just wouldn't notice if we swap buffers, I don't think. So that's coming at some point. There's more research to do yet. On some analytes, now you know some analytes are worse than others for this. And I think it's a strength of Nanopore that people do all kinds of things on it. People doing jellyfish and, weird things. And people who've never run a sequencer before are doing it. Right? So the variance is enormous on Nanopore, especially on MinION. We're not smashing up human genomes and doing the same protocol every time. So obviously there's going to be variance. But there are certainly some analytes, chicken is a good one, and others, some fish, that seem to be difficult. And they often have a lot of low complexity regions in them. So on some of those test reagents that we have, We're getting more than a 70% improvement in that. So I know this is annoying for people, that you can put a spindly killerfish on your nanopore, and then it just doesn't perform like that bacteria you did yesterday. So we're going to nail that. And to that point, so I had a very irate user earlier in the year, I won't say who it is, who put a very precious, endangered, I'm not sure what it was, but it was some kind of really ultra-rare sample. They committed it to a Promethean flow cell. And I think it's the time when we had a software bug that affected the channels. And he or she was really angry because they thought they'd lost the sample. Because obviously on most of the sequences, it's gone. Once you put it on the thing, it's gone. It's not gone on Nanopore. Right? We only sequence a tiny fraction of the molecules. The rest of it's just floating around in the flow cell. We haven't changed it. It's what you put in. So you can take it out again. You can slurp out the sample from Nanopore flow cell, and you can run it on another flow cell. There's no excuse, really, to lose a precious sample on Nanopore. And the tests we've done, you get like 80% of the yield on the second flow cell. So you shouldn't be losing samples on Nanopore. It's an inherently fault-tolerant system in that way, anyway. And you can even, if your library prep fails, you can pull out the library and do it again on the same molecules. You just have to go around the loop again. Perfectly feasible. All right. Good. So this is the bit I like, which is all the new boxes I'm going to make. I said you don't need new boxes, but I'm going to sell them to you anyway. Because they're better, just to emphasize that. It's not just an upgrade thing. Okay, Mark 1D, you've seen it anyway, it's out there on the stand. This replaces the current Min-ion completely, finally, after 10 years now, pretty much. And apart from looking like the communicator from Star Trek, which I think is quite cool, it's USB-C powered. It's much better temperature control. So for people doing field sequencing, it's really robust to temperature problems in field. No need for ice blocks or aluminium blocks or all that stuff. Really good. It's backwardly compatible with the current Min-ion flow cell. All that really means is it's got the same connector. It's got the same connector, so it's backwardly compatible. It will work with those. And as you've seen outside, we're going to launch this product shortly, where we've made a system that docks it to an iPad. So that really, in my mind, functionally replaces the Mark 1C. That's the integrated device. And this is, I wish we'd done this, but it wasn't available years ago. The key change here is the Apple processors, which have these GPUs on them. They're really good, and they can keep up. You've got keep up base calling. And we've now written an iOS-specific caller and an iOS-specific interface. We get a battery, and we get 5G and Wi-Fi. As you know, tech billionaires are trying to put 5G everywhere, and they're going to do it. They're going to do it. You're going to get 5G in the jungle. So why wouldn't you be streaming data up to a cloud to tell you what the sample is? Why wouldn't you do that? Well, this kind of device will do that. And you've seen it out there. It's on a frame, and the final device will have a kind of rigid, ruggedized slide-in cover, a snap-in cover that will be drop-proof and hit-proof, and so forth. And you can register your interest in that device now. That will replace Mark 1C. So that's pretty cool. And here is the actual running, it's a movie, but it's the running iOS interface for that, which we're showing outside as well. So all upgrades. Now, beer is coming, trust me, this is important. I could talk about ASICs for another hour. Just don't tempt me. I think it's true, I think it's still true, Keith will correct me on this blog, I think it's all true, still true, that all the other platforms rely on a third-party camera, a third-party CCD camera, an optical system. So they buy it from somebody, Hamamatsu typically, and they've got little or no control over the characteristics of that camera, and how many photons it can collect, and how much data it can dump. Really the design of their instruments pivots around all of that. And we don't do that, we design our own sensor, We design our own equivalent of the CCD in the camera, and it's called the ASIC. And making ASICs isn't easy. It's hardcore electronic design, and it takes years. It takes years. And if you make a mistake, it takes another year to fix the mistake. It's a huge investment. Well, we have custom ASICs in all of our devices, as you know. In fact, here they are. Bugger. It's in my bag. Could you just fetch my bag up, please? So we now have, finally, some new ASICs coming. And actually, new ASICs does mean new devices. And previously, we've called it the Smidgine ASIC. I hope I can find it. It's so small, so tiny. I put it in here. No, it's not that one. I bet I can't find it now. Typical. Oh, here we go. So last time I showed it, it was very early stage, and I put it on the end of my finger. It's on the end of my finger there. But I've got them here now. And here is an actual board. That's a CAD there. Here's an actual board with an actual functioning Smidgine ASIC on it. Give you an idea of the size. And we can actually make it smaller than that. That's a big one. That's a big one. The actual ASIC bit there is it's like 5 millimeters by 5 millimeters or less. And again, called the Smidgine ASIC. Now really, the ASIC is the heart of the machine. So that, and what we put on top, and then the chemistry, that is everything. That's the heart of our system, right? And I used to say to people, when I was allowed to, I'd say to them, when things weren't working, I'd say, no chip, no product, no job. So seriously, it's true, because that is everything. And that is our new Smidgine ASIC, which I'm very excited about. I'm going to talk about what we're going to do with it now. So it's different architecture. As you can see, we connect it to a board with nanopores on. And the version here has 400 channels. And it's a single mux. Now, what is a mux? If you think of a corridor with doors at the end, right? So single mux means there's one door. And when you open the door, DNA comes through. Now, the MinION you have has a 4 mux, so it's got 4 doors. But only one of them can be open at one time. So you can change the doors around. But this is a single mux. And it's very low power consumption. Really, really low power and low heat. In fact, we have to heat it up. We have to heat the thing up to make it work. That's how efficient it is. So that makes it really suitable for portable devices. Perfect. The things we've got really are compromises by comparison to this thing. So this is really the thing we should have made in the first place. But we've built all of our knowledge and expertise over the years into designing this. And it's now, and the big thing with an ASIC is when you do an end-to-end run, you put everything on and you run it, does it actually work? It does work. We get Q20 plus and we get Duplex. So that's a fully functioning DNA sequencing ASIC. Tiny mobile phone style power consumption on that. Minuscule and a very low format. So that really does open up the democratization of sequencing potentially, and protein sensing and other things. So Mark II MinION. This is now in active development because we have the board and we have the ASIC. This is the Mark II. And actually, when I first spoke about MinION in 2012, it was a completely disposable USB stick. And actually, this is now pretty close to that. And I'm not allowed to say this, but I'm going to say it anyway, in channeling Elon Musk. This is cheap. Obviously, it's cheap. So there's huge flexibility on pricing. So you can really think about pushing MinION into places where it's never been before. Now, we still have a little dongle with it, and all that's in there is a little interface chip that intermediates between the USB device and the MinION. It's nothing. You could, in principle, run this and throw it all away. And we'd send you another one, and you could do that again. And we thought about that with the first MinION, but it's actually pretty unethical to do that if you think about it, especially now. I mean, the aluminium, think about all the energy that went into making that aluminium case, right? You wouldn't do that now. But anyway, it's actually, with modern materials, we could make it fully disposable. And certainly the bit on the left there, you could just pop it in the tips bin and forget about it. That's how good it is. So this is really exciting. This is Mark II Mini. And that is coming very shortly. I think I've missed a graph here. Let me go back. No. Now, we're thinking for this, if I didn't say, 5 to 10 gigabases. That's based on the current chemistry system. So if we claw back that blocking and if we speed things up, it could be 15, it could be 20 G from that. And Gordon's going to kill me. We can make it cheap. It can be cheap. So pretty compelling. And we've shown it here plugged into a Mac. And that's because they have this processor now that's really powerful GPU on board, low power. You can run it for hours. You can do the base calling. You can do it all on the laptop or similar device. Really powerful. And then we can make this. This is Grongle, which is gridiron as a dongle, or Grongle. Now, Gordon isn't going to let me launch it with that name. But I bet that name catches on. And okay, so what's in here? So we can array these things. We can array them. Our trick has been to array flow cells, cheap flow cells, array them. And here we can do it again. And the box here contains really a heater to keep things warm, collects data, and roughly speaking, a current M2 laptop can keep up with the base calling. Hot pluggable, hot swappable, super cheap. It's the next generation of Mini. That's what it's going to look like. There's a little QR code there if you want to register interest in it. But we have another ASIC coming. We have another one. So the old ASIC, if you turn your Mini over, the current Mini, and you'll see it's got an ASIC on the back. It's a little grey square. Doesn't look like much, does it? That cost us 200 million to make that, something ridiculous. It's 15 years old. And it's got issues. So we have a new one now. And the new one is based on this architecture. That's what chip makers do. Once you've got an architecture, you can then scale it. And we're scaling it onto this new device. So again, low power, low heat. Different MUX architecture again. But what it does is it front loads the output. So you get the same amount of data as a Mini in half the time. And again, we think with optimization, those numbers will be larger. We can't say that today, but our gut feel is we can push those numbers up. So we're going to swap out the ASIC on the Mini flow cell. We're going to mostly keep the Mini flow cell format like it is for improvements. And it will be compatible with the new device outside. And I think the plan is that when you buy a certain number of flow cells, you'll get the device with that. Yeah? It'll just come bundled. Hope that makes sense. So pretty significant. So Mark II Mini and an upgrade to the existing one. But this format opens up a lot of interesting new ideas. And again, I can tell Gordon's going to kill me because it's so cheap. Because it's so cheap. It got me thinking about things, right? What you can do with it. So, right now we have a very active program to completely revamp the Voltrax device. I've looked at it, I've thought about it, I've listened to feedback. A huge amount of work's been done by the team, which we're going to leverage in the new device. And it's uplifted by the inclusion of this thing. So what have we done? Well, it's pretty much the same base unit that you have now, enhanced optics. But I've redesigned the flow cell completely redesigned the flow cell. So it comes ready to run. So all the reagents are preloaded in the bloody flow cell. So you go in your shop and you say, I want a ligation flow cell, or I want an extraction flow cell, and it comes ready to run. You don't need to do anything except add the sample. So it's a very nice, flat, thin preloaded, factory-made flow cell where you just add the sample and start your run. That's it. And as you know, those of you familiar with Voltrax, on this system, we can automate pretty complicated workflows now. The whole ligation prep, extractions, single-cell extractions, work's been done to do that on this sort of format. So it's sample in, no lab work for you. But the key thing is we've incorporated this sequencer into that device. So you plug in the flow cell and the reagent cartridge. When it's done the library prep extraction, we'll load the sequencer and then run it as a sequencer. So it's an improved Voltrax and a sequencer in one device. And we think that will be very useful in applied markets, for example, where they just don't want to do lab work to get an answer. And I am hoping to have that on the stand this time next year. And actually, 80 or 90% of the work's been done on the current system. And a lot of the rest of it is what we're doing anyway for this, because it's the same modular, hot pluggable format. So that's really exciting. There's a prototype flow cell, preloaded with reagents that we run. We currently run them now. So it's a reformatting in many ways, and that's coming. These are, again, you can take these out, and I think what we're going to do is you can sequentially load this with multiple samples. You can load it, take it out, put it into the grongle, and then load another one, take it out, put it into the grongle, and so forth. So that many-to-one and one-to-many mapping between sample and sequencer, I think, is going to be quite transformative. That's where that's going. So I hope that's not been too much spam, and there's been some juicy stuff in there, some eggs and Duplex. I mean, the main message is that the things that we dangled in front of you last year, most of them are now out the door. And the next big challenge, really, apart from incremental development, modifications and RNA, and those are all out the door as well. New devices, all great stuff. But the thing I want to fix is homopolymers. Then you can do Nanopore only. Why would you buy anything else? What's wrong with you? Nanopore only. That's where we need to get to. All right, and with that, I'm going to let Rosemary do a summary of releases and things. I hope that's been useful, and we'll take some questions. Thank you very much.
Where have you hidden the slide ticker? All right, don't have to look through your bag. All right, so we've got a lot. Clive has just talked about an enormous amount of R&D work that's very active. But just to give everyone a little timeline on how we're doing, the P2, the integrated one. Thanks, Clive. That is with developers now. We have the Min9 Mark 1D coming out late summer, again to our developers, and then we will actually start our early access P2I early access program later this year, so we can get it out to more and more users. Turbot we haven't covered today, but we will talk about it briefly tomorrow, and you've seen it at the stand. So Turbot's going to be out later this year, again to developers, as will the iPad case. And then this timeline wasn't quite long enough to get the Smidgine ASIC, but it won't be too long after this. Regarding flow cells, we've got R1041. Those have gone from early access to released over the last few days. So we get a lot of questions. When's it released? When can I start doing all my stuff? It's there. High Duplex early access is beginning as well, so please do sign up on our website. The RNA for developer access, sign up on the website, please. Well, actually, we don't need to say please. There are a lot of interest, so we can already tell that's coming. And then we will broaden that up during the summer as we scale up all of our production. On the kit side, it's endless. Kit 14, early access has gone to release. Rapid barcoding for PCR coming very soon. multiplex ligation kit coming very soon, Cas9 version 14, RNA early access, cDNA sequencing kits. We've had a lot of questions about the cDNA sequencing kits. When are they getting up-revved? Cyclomics, a few people have mentioned them today already. We are doing a Cyclomics early access launch as well. As are we doing 384 barcodes and 16S. On the software side, again, we are very, very active there. So Minnow went yesterday, 5 kilohertz, pod 5, that is out in the wild now. The new mods, the research release, out in the wild now. And Dorado updates out in the wild now. So the Dorado team can go and get a couple of nights sleep because they haven't slept for about 5 weeks. Everyone is then working really hard on Dorado integration. We all want to see you guys base calling everything in real time, being able to plug in your P24s and getting all of that data happening. That's what everyone's really focused on, getting all of the analysis on board. And the epitome. I know, we've hidden the epitome team down in the DAC cave, but please go and see them tomorrow. They really want to show you everything they've been working on, and it is easy enough for me to use, so you guys have got no excuse. And then we will continue all with the Minnow, so Duplex integrations, and really interestingly, workflow integration, so that you can kickstart a Minnow run, ask it to do an analysis at the end, and it will take care of everything for you. So hopefully with that, we can now end on the summary where we are on raw read accuracy, 99.5, Q22. Stu Reed has checked these numbers carefully for us. So that is with the 5 kilohertz. These are all the 5 kilohertz numbers. Duplex accuracy over Q30. SNP, indel scores, you've seen all of that. Telomere to telomere, we are now aligning against the telomere to telomere reference genome, thanks to the T2T team that have done all of that work. And of course, we're getting over Q50 consensus on our assemblies for bacterial, structural variation. Dan talked about this earlier today. It's as good as you can get it. And methylation accuracy of 99.7, raw read methylation accuracy. And so with that, thank you for all of your attention. Thank you.